Everything that we've been talking about so far in the course has been the theory and concepts behind production data analysis. We're going to switch over now and start to talk a little bit more about the practical considerations, and we'll take a look at some examples. As you've already seen so far, there are several different methods that we use in production data analysis, and the most comprehensive way to analyze production data is to look at all of these techniques in sequence and get a sense for what's going on. So what I'm going to do is go through each of these methods and talk about some of the practical considerations. And we're going to start with the ARPS decline curves. The ARPS decline curves, of course, have been around for many, many years. They basically provide the foundation for reserves evaluation and production forecasting in the petroleum industry. Many, many years ago, ARPS conducted a study where he looked at thousands of wells. And of course, if you recall, to do decline curve analysis, it's an empirical method. So it really relies on looking at lots and lots of data experimentally. And this is exactly what ARPS did. So he looked at high pressure wells, low pressure wells, reservoirs that produce oil, reservoirs that produce gas, water drive systems, volumetric systems, basically with the intent of gaining an understanding of what sort of decline curve properties one would expect for the different types of drive mechanisms and different types of fluid productions. So I want to talk a little bit about the results. And we can still use something like this today as a template in situations where maybe we don't have a lot of data to work with, and we need to come up with some sort of decline curve prediction of what that well is going to do in the future. So I want to start with the basic stuff here. If you recall, a b-value of 0 implies an exponential decline curve. And what ARPS found from the study was that single-phase liquid expansion, for example, that would be an oil well above the bubble point producing at constant pressure. Or gas at high pressure. And I mentioned earlier that a gas at very high pressure behaves a lot like a liquid that's single-phase. When the gas starts to become lower pressures, things change. But high pressure systems where we have liquid above the bubble point or gas, and again, it's not stated here, but producing at constant pressure, constant operating conditions in the reservoir will give us an exponential decline. And that shouldn't be a surprise because we showed theoretically that an exponential decline property would be expected if we're producing a single phase fluid at constant flowing pressure. What happens if we start to lower the pressure in an oil well below the bubble point? Well, what happens is we start getting gas coming out of solution. And that's, of course, what we call primary production in an oil reservoir, or solution gas drive. What's going to happen here is we're going to end up increasing the b-value in the system. And that's basically because we have more energy in that system. As soon as the gas evolves out of solution, it provides pressure support. The b-value can vary somewhat through here, and that can be controlled by things like relative permeability in the reservoir and geometry effects. For example, if the reservoir is capable of maintaining a secondary gas cap, in other words, there's a place in the reservoir where the gas can bubble up to the top, you'll tend to get a higher b-value in that reservoir because you're maintaining the gas energy in the reservoir. And of course, that's what you want to do as an operator. If you're producing that oil, you want to keep the solution gas inside the reservoir and maintain as much energy in there as you can. On the other hand, if all of that solution gas is produced away and there's no place for a secondary gas cap, or the reservoir is not operated efficiently and all of that gas is lost, the b-value is going to stay low and in fact maybe still very close to exponential. And of course that's not a good situation. You'd get less recovery that way. What happens if we change over to a gas? If we've got single phase gas producing again at fairly constant conditions, over the life of the well we tend to see higher b-values. So I mentioned earlier we're going to see something close to an exponential decline at high pressures. But as the pressure starts to fall, the gas will expand. And part of the reason for that is we have increasing gas compressibility at low pressures. And we talked about that earlier. We expect that because we know that gas has a very highly nonlinear compressibility as pressure drops, as pressure goes down. So at very low pressures, gas has a tremendous amount of energy that it didn't have at high pressure. Another area that ARPS did some investigation is with aquifer systems or edge water drive systems. And what he found was, again, we have additional energy in the system, so we start to see higher B values. So a B value of 0.5, for example, seemed to be a good predictor for effective edge water drive systems. Now, of course, this sort of decline property isn't going to last forever. In an oil reservoir, you're going to reach a point where the water breaks through, and interestingly enough, that will go back to an exponential decline if you start to analyze just the oil phase production once we start to get breakthrough in an oil well, either gas or oil or water breakthrough, we go back to exponential decline properties. One of the problems with trying to use decline curves to do long-term oil production forecasting is that there's too many parameters to have to predict over a long period of time. If you can imagine, if you've got just a little bit of data at very early times, we really don't know when pressure maintenance is going to occur, when we're going to get these energies coming in place. It's going to be very difficult to do a long-term production forecast on an oil well. And this is something that's always been a bit of a challenge in the industry. Gas, on the other hand, is a lot easier because a single-phase gas system will typically be a single-phase gas system for the whole life of the reservoir. And the energy of the gas dominates the whole system. So we tend to have a much easier time or much more confidence in our predictions, long-term predictions of gas production for gas reserves analysis than we do for oil. And that's one of the challenges of analyzing oil is we have to deal with these much more, there's potentially much more unknowns in the system, especially early in the life when we don't know what's going to happen later on. Moving forward from there, there were some studies done on layered reservoirs, and a lot of this work was done by Fetkovich later on. And Fetkovich looked at layered systems, specifically in the Hugoton Reservoir, which is a massive reservoir that covers 4 states in the United States. And what he found was that layered systems tend to have higher B values as well. And you can see the B values are just continually going up as we go down the list. And what causes higher B values in these layered systems? Well, if I can draw a picture of a 2-layered system, if we have a well, and we're going to say it's perforated in 2 separate layers. And I'm going to say that one layer is a limited system that has a high permeability. And the other layer is an extensive system that has a low permeability. And of course, this is a simplification of what's really going on in that system. However, a lot of layered reservoirs can be approximated with a 2-layer analogy like this. And what happens if you think about a system like this is the high permeability part of the production is going to occur first and can contribute at higher pressures. And you won't see much contribution from the low permeability layer because it doesn't have as much flow capacity. In fact, you may see no contribution from this until later on. Later on, when the pressures draw down in the system, the lower permeability system will start to contribute more, and there'll be a recharge effect. The recharge effect has the effect of driving up that B value in that system. Okay, so the more heterogeneity, the more contrast there is between the permeabilities of these 2 systems. And of course, there may be other layers that are added in there as well. The more energy you're going to have that's delayed and recharged into the system as time goes on. And that's going to drive up the B value. So these layered systems could be anywhere from 0.5 all the way up to 1.0. 1.0, of course, is a harmonic decline. And we see some harmonic declining wells that are layered systems. One thing that's not shown on here is horizontal wells. Horizontal wells will very often have high B values as well. Okay, so sometimes those things will come into play as well. I want to spend a little bit of time, and you can see there's a separation here. ARPS and even Fetkovich never really got into the discussion of transient analysis. In fact, Fetkovich made the statement many years ago that we really shouldn't be using ARPS decline curves at all for transient systems because really this stuff is designed only for boundary-dominated flow. One of the challenges that we have now in the industry is that there's a lot of production that occurs from very, very low permeability reservoirs. In fact, when we get into tight and unconventional gas systems, we're talking about very, very low permeabilities, sometimes in the microdarcy or even nanodarcy range. So we're going to start to see, and we're already seeing it, lots of production decline analysis that's occurring with very, very low permeability reservoirs. And the implication of that from the ARPS perspective is that we have B values that go higher than 1. So Fetkovich always said, never use B values higher than 1, but that's what we're seeing. We're starting to see that the B values, if we want to use these decline curves, they have to be higher than 1. And there is a way to properly use decline curves with B values or hyperbolic exponents that exceed 1, but we've got to be careful, and I'll talk a little bit about that a little later on. It can be dangerous to apply these techniques if you're not applying the proper constraints. Okay, from a practical point of view, let's talk a little bit about the advantages of traditional decline curve analysis. A lot of the discussions in the theory part of the course centered around the modern methods of decline analysis where we use the analytical solutions. One of the advantages of always going back to this empirical method, at least as a complement or a comparison, is that it's easy and convenient. It doesn't require any assumptions about the system. For example, I can put a decline curve on any trend that I see in production data. Analytically, I have to make assumptions about that system before I can analyze it. Empirically, I can analyze anything. So that can be an advantage because we know that real reservoirs are very complex. So it's nice to be able to have a method that I can apply just based on the trend of the data. It's a very real indication of well performance. So it's a good way to do, for example, P90 or proved reserves, because it's really showing you where that well is going. So I think that's an advantage as well. And in fact, traditional decline curves have been the cornerstone of reserves evaluation in the petroleum industry, at least in onshore North America, for many, many years, and will probably continue to be so. But I want you to be aware that there are some limitations of traditional decline curves. And these are important, and I think we need to be aware of these things, especially when we start to get into more tight gas and unconventional gas through time. There's an implicit assumption of constant operating conditions. I think I mentioned this before. Anytime you're going to change the flowing pressure or change the conditions in the well, of course your decline properties are going to change as well. And one of the advantages of looking at the analytical methods in addition to these traditional decline curves is that the analytical methods can take into account those changing operating conditions. And I'm going to show you two examples in a minute that illustrate the limitation of operating conditions. Sometimes we have non-unique results for traditional. In fact, we frequently will have non-unique results if we're either in a case of very early time production, maybe we only have a few months of data, or we have transient flow from tight gas or unconventional gas. And I'm going to show some examples for this as well. And then I suppose the final one is that really traditional decline curves are nice, they're easy to apply, but they don't really give you too much information about the reservoir. If I want to know what's the permeability, is this a stimulated well, what sort of drainage area do I have for this well, what's the oil in place, what's the gas in place, I can't learn those things just from doing decline curves. So we need to be aware of those limitations and understand that there's other methods that are out there. All right, so here's an example, and in this particular example, what we're going to see, I'll give you the answer before we start, but you can keep it in mind as we go, is that the decline curve is going to overpredict reserves, and you're going to see why in a minute. So the screenshot is illustrating here a semi-log graph of production rate versus time. This is a gas well, and we have rate versus cumulative production on the bottom. If you were just to take a quick look at these two pictures, I think most people would agree that that shows a fairly nice semi-log straight line and would suggest that we have an exponential decline in this data set. This is the same data set. One thing that is a little bit of a red flag, and if you're an experienced reserve evaluator, most experienced reserves evaluators would key in on this, is that we have a limited amount of production and we're forecasting a long ways, which is usually a bit of a no-no. We don't want to have this sort of situation where we're forecasting more than 3/4 of what's been produced so far. However, all other things being equal, it looks like an exponential decline. And we predict an EUR of 9.5 BCF using this method. This plot, what I've done is I've taken that same rate versus cumulative graph and I've just included the flowing pressures on there as well. So the flowing pressures are shown on the right-hand axis, the production rates are shown on the left-hand axis. And what I want you to notice about this picture, this is a very easy thing to do if you have the pressures. It's not that difficult. I mean, all we're doing is showing the data together. But what I want you to notice is that the pressures are declining fairly steeply. And when we reach a certain point, the pressures simply won't be able to go down anymore. If we have a situation where pressures are falling, remember the golden rule of decline analysis is that my prediction of the trend in the future is valid so long as the conditions in the future are the same as they were in the past. In other words, if my pressures were declining in the past, this forecast is valid as long as the pressures keep declining at the same rate. Okay? So that can happen for a certain amount of time, but we're going to reach a minimum pressure and then we can't drop the pressure anymore. Right? There's going to be a line pressure or a system pressure that I can't drop below. And then, of course, what's going to happen to the production when we reach that point in time? Well, everything's going to drop very dramatically. Okay, so there's no way that past about this point in time, and we can extend this down further, and you'll see that you'd reach about 0 pressure after about 6 BCF. The production forecast simply is not valid through that last little part. So our prediction of 9 BCF is an overprediction of what's going to happen. The true EUR is going to be more like 4.5 BCF, which is half. So it makes a very, very big difference when you include the effect of the pressures in this case. Here's a second example. In this example, we're going to see that the decline underpredicts reserves. And in this particular case, we have much more production to work with. So our assessment of exponential decline is actually pretty robust, I would say. Okay, we have 2.2 BCF, and we're forecasting out to about 3 BCF. I don't think any reserve evaluator would have a problem applying this decline curve to this data and saying, yep, that's my P90 reserves. Okay, or that's my production forecast. So this seems to work okay. If you look at the early time part of the data, you can see there's some things going on. Obviously, the operating conditions are changing through here. We have a constant production rate at the beginning, and then there's a drop in production, and then it goes into more of a constant percentage decline after that. What are the reasons for that? Well, we're probably battling some sort of maximum rate limitation through here, and then I'm not sure why it drops, but there's obviously some operational things happening with that data. Not very uncommon. We're going to see that a lot in gas wells, particularly where we're producing to some sort of gathering system. It's very dynamic. There's things changing in the system. It's going to cause a change in the properties. I haven't talked yet about the flowing material balance, but we're going to get to that a little bit later. This is an analysis of the same data using the flowing material balance method. And all you really need to know about this method is that it includes the effects of the flowing pressures. So instead of just looking at the rates, it includes all the flowing pressures in the system as well. And what we see is that the original gas in place is 24 BCF. Now this is a little bit of a surprise given that this well is only expected to recover 3 BCF. Normally in gas reservoirs, we would expect a much higher recovery than that. How is it possible that I'm leaving most of that gas behind? I should be able to recover much more than 3 BCF if indeed there are 24 BCF in place. Okay, so the interesting thing about this is there really is 24 BCF in place. Why is it that we can only recover 3 BCF? Well, when you start to look at all of the data together, you get the picture of what's going on. And this is our full data chart with our gas production rate versus time and our flowing pressures versus time. And our flowing pressures, you can see, have some interesting characteristics, at least through the last 3/4 of the data set. They're increasing, and they have a fairly high value already. And what's actually happening in this example is this well was drilled into an area where there was a gathering. Well, this well was drilled earlier, and the gathering system that was accommodating this well's production was inundated with additional gas from new wells that were drilled into reservoirs with higher reservoir pressure. So essentially, this is what we call line pack. You get a situation where this well gets backed out of the system because there's too much gas being drawn into this gathering system and not enough capacity to accommodate it. And that's why our pressures start to go up. Normally, we don't expect to see system pressures or back pressures in a system increase through time. That's not a very good way to operate a system. But in this particular case, that's what happened. We would never have known that if we hadn't looked at the pressures and the rates together. So the moral of the story is we need to understand both the production rates but also the flowing pressures, because they're sort of tied together in a very intimate sort of way. When one of these things changes, the other one's going to respond. So if we only have access to the production rates, we're only getting half the story. Okay? And in this case, our assessment of 3 BCF is actually correct under these conditions. But it misses the fact that there's a whole lot more gas in place, unrecovered gas in place that's down there. And this is a huge production optimization candidate. You never would have noticed that if you didn't have access to the flowing pressures. So very important to have both those sets of data available. Okay, finally, our third example, we're going to talk about illustration of non-uniqueness. And this one's pretty straightforward. When we have early data, in other words, maybe only a few months of production data, all decline curves look the same. This is one of the big challenges we have with decline curves. Okay, you can put a hyperbolic decline curve with a low B value, a hyperbolic decline curve with a high B value. If you only have a limited amount of data, they look identical. So how do you know which way that well is going to go? Well, the answer is you have no idea. You have to keep producing it to find out. Or you have to use the rule of analogy, which is what ARPS tried to do by coming up and analyzing different types of wells under different conditions. But we can see that all 3 of these decline curves match this data very nicely, but they all produce very different EURs. This problem is magnified when we have transient production due to tight gas and unconventional gas, because we'll start to see this situation, but these curves may even go out further in time. So we have a situation where the expected ultimate recoverables are very much unknowns because of the shape of these curves. And there's really no way to know other than letting the well produce and seeing through time how it's changing.